Hello. So today we will see the basics of the antennas, the antenna beam pattern, how the antenna beam pattern looks, how to plot the antenna beam pattern in MATLAB. So let us start. We generally don't consider a single element antenna because if we are considering the single element antenna, the beam pattern will not be sharp, or the direction of the antenna or the direction of the beam will not be sharper. Therefore, we won't get much details with respect to the angle. Therefore, let us consider or start with the two antenna case. So here we can consider this is the set of the antennas. We have two antennas, antenna A and antenna B, or we can say it as the antenna elements. So this scenario can be considered as a radar case or some communication case. In case of radars, we transmit the signal and when we receive the signal. In case of communications, the transmitter is somewhere else and then we just receive it here. We can consider any aspect or any type, but just the concept will remain same. So here there is something which is being transmitted from this direction, there is something which is being received from this direction. So this is the direction of the signal. So there is a wavefront. The wavefront is perpendicular to the direction of the signal reception. So if this is the signal reception direction, the wavefront will be perpendicular to this dotted line. The wavefront itself is making the angle of theta with this horizontal line, or you can say the antenna base. So with respect to this, if you're considering the signal reception direction is if this is the signal reception direction, the wavefront angle will be 0. The wavefront will be totally horizontal and this theta will be 0. I will repeat, if the wave is coming in this direction, the wavefront will be having the 0 degree angle or theta will be 0 degrees. Now considering the signal is coming in this direction and wavefront is making angle of theta with this horizontal, we can say the signal received at the antenna A, if we are considering as a reference, then the same signal will reach at antenna B with some delay. If we are considering the antenna as a reference, then the signal which is received at antenna B will be having some delay, and that delay we will be in terms of uh, this angle. I will depend on this angle. So if these two antennas are separated with a distance of d, then that delay will be in terms of this distance is d sine theta. I can say it as meters. If this is d meters, this is d sine theta meters. However, the delay needs to be converted in terms of the radians or the seconds basically. So if you're considering the signal as signal length is lambda meters, if the signal length is lambda meters, that corresponds to 2 pi. Then this delay d sine theta corresponds to d sine theta by c. This delay corresponds to d sine theta by c. So maybe this will elaborate further. Now, this received signal at both the antennas is complex demodulated. The complex demodulation is, for example, is something like when the signal received is maybe sine or cos, we just multiply it with the local oscillator. If received signal is assume it as cos, we multiply it as sine and then we multiply it as cos as well. So we get two different signals. So that two different signals are called as one complex demodulated signal. A complex signal can be represented in this format: e raised to j 2 pi fct, which is cos 2 pi fct plus j sin 2 pi fct. So this is done at both of these antennas further. Now finally, these two signals or these complex demodulated signals are added. But let us simulate or let us consider how these two signals look like. Assuming zero delay at this antenna, because this antenna is assumed to be as a reference and there is some additional delay at this antenna. So assuming zero delay at this antenna, we assume the signal received at this antenna A is e raised to j 2 pi fct. Similarly, the signal received at antenna B will be having some time delay, which is this is just t delayed by some this additional time, d sine theta by c. D sine theta is in meters, c is in meters per second. So this ultimately d sine theta by c is in seconds. So it is distance upon speed will be giving the time, the additional time required to travel this additional distance. So the received signal at B is e raised to j 2 pi fc t minus d sine theta by c. Okay. So finally, these two signals are added and we get some received signal r of t, which is dependent on the time, or we can say which is the signal is dependent on the theta mainly. So this is the signal uh, received at the receiver. Finally, uh, generally in case of the antennas, this d is maintained in terms of lambda. So as we know, f by c is 1 by lambda. We can replace these things in the above equation and we can get this equation. We can get this equation. Now we are interested in the energy which is received at the receiver. We do not consider anything about the actual signal. So we consider what is the energy received because the beam pattern is in terms of the energy or in terms of the powers. So the energy is, we cannot say it as negative energy or positive energy, just we use the magnitude of the received energy. So let us take modulus of the received signal. So if we take modulus of this received signal, so this part will become 1 because it has magnitude of 1. Cos square theta plus sin square theta becomes 1. So this part has a magnitude of 1. Remaining is this part. And this, now as I told, we generally consider the D, the antenna separation or the distance between the two antennas in terms of the lambda. Now here let us consider the antenna separation is lambda by 2. The lambda is a wavelength of the signal that we transmit. Remember, lambda is a wavelength of the signal that we transmit. Therefore, we will here assume that d is equal to lambda by 2. Phi d is equal to lambda by 2, or it should be uh, even less than lambda by 2 because we need to satisfy the Nyquist criteria of the sampling in terms of the space domain. We cannot use it more than lambda by 2. We need to go below lambda by 2 with respect as per the Nyquist rate. Now here, when we put d is equal to lambda by 2, finally we get this equation. Now manually, if you take a pen and paper, we can put different values of theta and then we can find out what will be the value of the received signal. You can put any values of theta, like for example 0 degrees, 90 degrees, 180 degrees, minus 90 degrees, or minus 180 degrees. We'll be getting different values and we can plot the theta versus those values. That is theta versus magnitude of the received signal. Now theta, as told, theta is varied to plot the beam pattern. Now in this case, we have simulated I have simulated this signal in MATLAB, or we can simply say we can plot this beam pattern in MATLAB instead of doing all those manual calculations. Either we can plot or implement this equation in MATLAB, or simply we can implement this equation itself in MATLAB, or this equation itself in MATLAB. So I implemented this equation in MATLAB. We can see how the beam pattern looks like. So this is the code written. Here we are varying the theta from 0 to 2 pi in radians. Lambda, we are assuming some 1 because anyway further that lambda will be getting cancelled, or d is in terms of lambda. So we are assuming d it is lambda by 2. This is the received signal 1 e raised to j, and this all. This is what we already implemented. We are here we are implementing finally this equation, or we can say this equation here in MATLAB. So finally, we are plotting a polar plot of theta versus absolute value of the received signal. We want absolute value. We don't need the negative or positive. We need just a positive or the received signal's energy, we can say. Energy or a positive voltage. So let us run this. This is what the antenna beam pattern looks like. Now, remember one thing. This indicate the angle. These indicate the angle, the circle. So this is 0 degrees, this is 90 degrees, this is 180 degrees, and so on. So we can see the signal direction is maximum, or the signal value is maximum in the 0 direction, which is the magnitude is 2, because this vertical line indicates the magnitude. So at 0 degrees, the we get the maximum magnitude, and at 180 degrees, we get maximum magnitude, and at 90 degrees, we get zero magnitude. So this line, or you can say this line or these cuttings indicate the magnitude level. That is 0.5, 1, 0.5, 2, 0.5, 1, 0.5, and 2. So remember one thing, in case of our diagram, the 0 degree is actually in front side. So we can say simply this 0 degree is in this direction. This is the wavefront direction. So beam pattern is something in this direction. I can show that to you once again. So it's something like this. This is the antenna beam pattern. If you can see, this is for 3 element case. So in this case, we are using d lambda by 3. So basically, this is 0 degree direction, and we are getting this. Now, whatever we are seeing is for 2 element case. Similarly, if we go for 3 element case, I already have this equations here. So in 3 element case, we have 3 elements of antennas. As I told, this will be theta. This is wavefront. This is the target direction. This is the signal direction. So this is d sine theta. This is 2d sine theta. These again, two the separation between the antennas is d. Now further, we can say, taking antenna A as a reference, and then we can assume that the delay at this antenna is 0. Further, at antenna B, we are getting additional traveling distance is d sine theta, and at this antenna, the additional traveling distance is 2d sine theta. So the received signals at antenna A is, again, this is the complex signal, and at antenna B, this is t minus d sine theta by c, and again at B, at antenna, it's actually c, which is t minus 2d sine theta by c. So further, we add all those signals. As I told, we can replace f by c with 1 by lambda. We'll be getting finally these equations. We can again take e raised to j2 pi ct common, and then we take magnitude of this received signal. Magnitude of this becomes 1. Finally, we get these things. So we have 3 antennas here. So we will take this lambda, d is equal to lambda by 3, and further we can simplify this equation. So finally, here we have taken some element as common to form some equation, and finally we're getting this as equation. So finally, we'll use d as lambda by 3. In case of a 2 element antenna, we use d as lambda by 2. Here we'll be using d is equal to lambda by 3. So to avoid the side lobes. So basically, we can implement this equation for 3 element case, or we can implement this equation itself for 3 element case. Or this equation itself for 3 element case. Finally, the beam pattern will be same as what we have the 2 element case antenna. However, the beam will be sharper. In case of 2 element antenna, this maximum magnitude we will be getting it as 2, but in case of 3 element antenna, the maximum magnitude we are getting it as 3. When we go for more number of antennas, the beam directivity will be more. The power radiated in any direction, this particular direction will be more, because when we go on increasing the antennas in the horizontal direction, the directivity of the beam increases, or the beam becomes more sharper. If we can use 4 antennas, 5 element antennas, 6 element antennas, this beam will point more, or the power radiated in this 0 degrees and minus or 180 degrees will be more. So this is what the basics of the antennas. You can, if you want, you can see this code. It's very simple code for 2 element case, and you can implement the same in MATLAB. Thank you. If you have any questions, you can write in the comments. Thank you.